Jai Hind to all of you. I am Dr. Sulekha Saxena, Assistant Professor, EC Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today, we are going to discuss the timing diagram of 8085 microprocessor. This topic is covered under the subject Microprocessor and Microcontroller of AKTU syllabus scheme for ECE third year students. So, first of all, as we all know that 8085 is an 8-bit microprocessor which performs various functions based on instructions provided by user. So, an instruction consists of two parts, that is opcode plus operand, and the time taken to complete one instruction is defined by the timing diagram. An instruction, as we all know, consists of two parts, opcode and operand, and the way a microprocessor fetches opcode or operand is divided into various machine cycles. So, an instruction cycle consists of various machine cycles, which can be minimum one machine cycle to maximum 5 machine cycles. Machine cycle is basically the time required to complete one operation from microprocessor. And one machine cycle consists of 3 to 6 T states, where T state is nothing but one time period taken by microprocessor. So, as we all know that 8085 is a microprocessor which runs in frequency range of around 3 megahertz. So, one time period or one T state is nothing but 1/3 microsecond, and the time is specified not in the unit of second, rather it is specified in terms of T state, which is equal to one time period. So, now we talk about various operations. So, the time required to fetch opcode from memory is defined as opcode fetch machine cycle, and the time required to read or write data from memory is defined as memory read or memory write. Similarly, the time required to fetch data from IO is defined as IO read or IO write. So, in overall, there are broadly 5 machine cycles that are defined for any microprocessor. So, in this lecture, we will cover the various timing diagrams as well as the description of each timing diagram with respect to T states. So, as we have discussed, the time taken by each instruction in graphical format is defined as the timing diagram, and basically single operation, that is one machine cycle, consists of read or write data from IO or memory, and for this purpose there are 3 status signals, that is IO/M bar, S1 and S0, and the basic combination of these signals will generate 5 type of machine cycles. The combination of these status signals, IO/M bar and control signals for each machine cycle is defined in this table. In case of IO/M bar, when the signal is 1, we are accessing data from IO, and when it is 0, we are accessing data from memory. S1 corresponds to read and S0 corresponds to write signal. Similarly, for read operation, read bar is 0, and for write operation, write bar will be 0. So, using this concept, now we will define the various cycles. For starting 4 operations, that is opcode fetch, memory read and memory write, for these three operations we are fetching data from memory. So IO oblique M bar is 0. For read operation S1 is used and for write operation S0 is used. So for memory read S1 is 1, whereas for memory write S0 is 1. And in case of 1-1, which is a special cycle, opcode fetch is done. So now we talk about the control signals. When we perform read operation, read bar will be 0, and when we perform write operation, write bar will be 0. And opcode fetch is also memory read, but in memory read we are fetching opcode from operands from memory, whereas in case of opcode fetch we are fetching or reading opcode from memory. So in case of opcode fetch also read bar will be 0 and write bar will be 1. Now for next 3 cycles, IO read, IO write and INTA, we are fetching data from IO. So IO oblique M bar will be 1. For IO read operation S1 will be 1, for write operation S0 will be 1, and for interrupt acknowledgement S1 S0 both are 1. And in the same way the control signals for read will be read bar 0, for write bar 0, and for interrupt acknowledgement INTA bar control signal is used. So INTA bar will be 0, whereas all other signals are inactive. As these control signals are active low, so when these signals are 1, that is inactive, and when 0, that is these signals are used. Now in case of bus idle machine cycle, means when there is no operation performed, that is an special instruction DAD, which is 16-bit addition, bus idle cycle is used. So buses will be remain in same state and this cycle will be done with memory. So IO oblique M bar will be 0. Since no operation will be done, it is 1 0 and all the 3 control signals are 1 1, that is all 3 are inactive. So no operation is performed by microprocessor. In case of acknowledgement of RST and trap, RST and trap are hardware interrupts which comes from IO. So it is IO oblique M bar is 1, and since acknowledgement of interrupt acknowledgement, so it is 1 1, and all these signals are inactive, so 1 1 1. And for halt and hold, IO oblique M bar will be in high impedance state, that is tri-state. It is a state wherein the connection is there but there is no data transfer. So it is high impedance state. When the signal is 0 0, INTA bar 1, it is halt, and for don't care, it is hold. So this is the overall combination of various machine cycles, and out of all these, the most important machine cycles that we will use in our instruction are opcode fetch, memory read and memory write. So now we will see the various signals which we use in case of timing diagram. First of all, the timing diagram is with respect to time, and time is represented in terms of clock signal. So the clock signal is defined as a cycle of 1 and 0, and in case of ideal clock cycle, it consists of 0 rise and fall time, and 1 t state is nothing but 1 time period. And since practically it is not possible that without any delay the signal reaches from 0 to 1, so there is a finite rise time or fall time, and hence the practical clock cycle will look similar to this diagram. So we use first of all the very important, that is clock signal, and with respect to clock signal we draw all the signals and buses, and for signals we use single line, whereas for buses we use double line. For logic 0 we use this type, for logic 1 we use this signal, and for tri-state we use this type of signal, not 0, not 1. For group of signals, we use double line and the change of bits will be shown by cross. So, all the buses will be shown like this, and when there is a valid value, it is shown by this cross symbol, which means some values are changed from 1 to 0 and some are changes from 0 to 1. When there is a high impedance or tri-state, it is shown by dotted lines. Now, when we talk about different buses, that is address bus, data bus and all the signals. So, the clock signal is shown similar to this, or we can draw it in a different way also, like this. We have to draw one complete cycle, just one complete cycle. So, we can show clock signal like this only. Now, from the above discussion, we can say that the timing diagram is defined in terms of machine cycle, that is nothing but T state, and T in this state is nothing but one time period or one clock period of microprocessor. The time required to complete one operation of accessing memory or IO is called as machine cycle, and machine cycle is broadly divided into opcode fetch, memory read, memory write, IO read, IO write, interrupt acknowledgement, halt, hold and reset. Each machine cycle is defined in terms of several T states, and the combination of one or several machine cycles will consist of one instruction cycle, which is nothing but the time required to complete one instruction execution. So, in 8085, one instruction cycle may consist 1 to 6 machine cycles, and one machine cycle may consist 1 to 5 T states. Now, when we divide an instruction into two parts, opcode and operand, the time required to fetch opcode from memory is called as fetch cycle, and the time required to fetch operand from memory is called as execute cycle. So, one instruction cycle consists of fetch cycle and execute cycle, and it is always specified in terms of clock signal. So, as we can see, one instruction cycle consists of 1 to 5 machine cycles, and one machine cycle consists of 1 to 6 T states. So, in case of 8085, there are basically 7 machine cycles which are defined in terms of T states. The most important one is opcode fetch, which is always there in each instruction, and opcode fetch varies from 4 to 6 T states. Normally it is of 4 T states, but in some special operations it is of up to 6 T states. For memory read, memory write, IO write, all are of 3 T states. Interrupt acknowledgement machine cycle consists of 6 plus 6, that is 12 T states, and bus idle machine cycle vary from 3 or more T states. So, we will see one by one all these machine cycles. First of all, that is opcode fetch. In opcode fetch, the microprocessor fetches opcode from memory. So, in this case, IO oblique M bar will be 0 and S1, S0 both are 1. The signals which we draw in each machine cycle timing diagram are address buses, data buses, status signals and control signals. So, before reading this diagram, I want to explain each signal in detail. We have already seen how we draw clock signal by one complete cycle. So, this is one clock period, one timing, then second and so on. Now, what about buses? The high order address bus A8 to A15 requires at least 3 T states to load complete address bus. So, it requires T1 to T3 T state to load higher order address bus, that is A8 to A15. The lower order address data multiplexed bus AD0 to AD7. In this bus, first machine cycle is required to load address A0 say A7, and after that in second machine cycle data is there. So for first cycle ALE is 1, data is loaded in this bus, and after that ALE will be 0. Now in case of read or write, when there is a read operation, peripherals give data to microprocessor, and peripherals are slower as compared to microprocessor. So data requires some time to load. So there is a floating state, and after that data will be available on data bus. So in case of code, there is also read operation, so there is a floating state. And once read bar is 0, then only read is available. So in second cycle, once read is 0, after that the data will be available on the bus. And for this IO oblique M bar, S1 and S0, we can club these signals and make it common from starting to end 0, 1, 1. So in this way we can draw a timing diagram. So in case of opcode machine cycle, 3 cycles are required to load address, and after that 1 machine cycle is used to decode the opcode. So minimum timing for opcode fetch machine cycle is 4 T states, and when there is some extra operation required like the 16-bit date addition, stack to write data onto stack, and some other 16-bit machine instructions, this instruction size may vary from 4 to 6 T state, because 2 T states extra are required to decode some extra operations. So normally opcode fetch is of 4 T states. So first of all I have drawn 4 T states, that is 4 clock period. And then higher order address bus will require from T1 to T3 state, and after that unspecified work, because the work is specified by opcode, will be done in 4th T state. Then lower order address data multiplexed bus. In first T state, the lower order memory address will be loaded in T1 cycle. Since this is a read operation, data is read from memory to processor, and memory is slower. So there is a wait state which is incorporated by this floating state, and after that opcode is available on data bus. So T2 and T3 are fixed for data bus. Next is ALE signal. Since address is available in T1 machine cycle on AD0 to AD7, so ALE is 1 in T1 state, and after that it becomes 0. What about read bar? Read bar is active low once read operation is performed. Since read is performed during T2 T3 machine cycle, so read bar is initially high, then it becomes 0, and after it becomes 0, then only the data is available. So this is shown by this trigger signal, and once this data is completely read out, this signal is again become high. And IO oblique M bar, S1 and S0 can be drawn from starting to end as same, and we can write value inside IO oblique M bar 0, S1, S0, 1, 1. So in this way a timing diagram is prepared in case of 8085. So it is a graphical representation of address, data, control signals and status signals with respect to T state. So this is a very important timing diagram. Now we will see the timing diagram of transferring a byte from memory to microprocessor, or we can say that it is memory read operation. Memory to microprocessor, that is memory read. So once a byte is transferred from memory to microprocessor, it shows 5 different signals. At T1, higher order address bus is placed on A8 to A15, and the lower order memory address is placed on AD0 to AD7, and at T1 ALE will be high. and IO oblique M bar goes low. During T2, read bar signal becomes low, which activates the data, and the data is read from T2 to T3 states. So during T3, memory is enabled, then instruction 4F is placed on the data bus and transferred to ALU. It causes the read signal to again goes high, and during T4 machine cycle, the machine code or the opcode is decoded, so the unspecified work is written in higher order address bus. So this is an example of opcode fetch or memory read machine cycle. Basically, we are fetching opcode, so it is opcode fetch. And if we fetch data, then it becomes operand fetch. So now we will move towards memory read or operand fetch machine cycle. In case of memory read, IO oblique M bar will be 0, S11, S00. And since we are reading, so read bar will be 0 and write bar 1. And since we are just reading data, so there is no operation of decoding opcode, and hence it requires only T1 to T3 machine cycle. The T4 machine cycle, which is there in opcode fetch, is for decoding. So T4 machine cycle, the machine code or byte is decoded by the instruction decoder. But in case of data, there is no decoding operation, so T4 machine cycle is not required. Hence, the opcode, except opcode, all the other data read or write operations from memory or IO are of 3 states only. If we write any instruction which consists of fetching data from memory, it consists of 2 machine cycles, opcode fetch plus memory read. Like if we write an instruction MVI A, 32. So this instruction consists of 2 operations. MVI A opcode fetch plus to read data from memory 32s of memory read. So any instruction which requires a memory read, opcode fetch must be there. So the total machine cycles will be 4 for opcode fetch, 3 for memory read. So total 7 T states to execute an instruction. So first of all, we will see the memory read and then we will see the complete timing diagram. So all the signals will remain the same, that is clock, higher order address bus, low order address data multiplex bus, ALE, IO oblique M bar, S1, S0 and read bar. Only 4th state will not be there. So we have drawn 3 clock cycles, and with respect to 3 clock cycles, T1 to T3 low complete T states is required to load higher order memory address. Then during T1 ALE will be 1 and low order address is available on 0 to 87. After that, since we are using read operation, so data is again moving from memory to IO and memory is slower. So there is a floating state, and after that, once read signal becomes low, the data is available on data bus. IO oblique M bar S1 S0 is same for starting to end. It is 0, S11 and S00. And read bar signal becomes low during T2 to T3, and once data is completely available on data bus, this signal will again become high. So I hope the diagram or the timing diagram of memory read is quite clear to all of you. Now, if we draw a timing diagram for MVI A, 32, so it requires 2 cycles, opcode fetch plus to fetch data 32, it requires memory read. So it requires opcode fetch plus memory read. Opcode fetch is of 4 T state and memory read is of 3 T states. So total 7 T states. So it's easier to write the numbering with T1 to T4 only or T1 to T3. We can also write it as T1, T2, T3, T4, T5, T6, T7, but then it is quite difficult to remember. we can easily learn this diagram with respect to the numberings that higher order address bus requires T1 to T3. Lower order address bus is available on T1 only. Data is available from T2 to T3, and that's why in each machine cycle we will start the numbering from T1 to T4, from T1 to T3 and so on. So the 4 T states are initially for opcode fetch and then next 3 for memory read. So we have drawn 7 clock cycles. If we write MVI A, 32, during the starting 4 machine cycles 8085 decode the opcode and find out a second byte is needed to be read. So T1 to T3 during first machine cycle is required to load the address. Say the address is 2000. So the higher byte 20 is available on A8 to A15 during T1 to T3. And the for T1 machine cycle, it's decode operation that is unspecified. Then 80 say 87 during T1 machine cycle, the lower order address bus byte that is 00 is available on address bus. Since it's a read operation, so there is a floating state. And after that, once read is 0, the data is available on data bus, which is opcode 3E. And after that, it is remains in floating state until next machine cycle. Okay. During first machine cycle, ALE will be 1 and after that it becomes 0 up to 4. IO oblique M bar is 0 and S0, S1, 1, 1 and read bar is low from T2 to T3. So 4 T states are required for opcode fetch. After that, we will draw memory read in a similar way. T1 to T3 for higher order address. Then during T1 lower order address, since read operation floating state and then data which is 32 as this instruction, so 32 bit data. ALE is 1 during T1 and after that it is 0. IO oblique M bar S1 S0 are 0 1 0 and read bar is 0 during T2 to T3. So I hope it's easier to understand the timing diagram of one complete instruction by combining it in separate sections. So we can draw the timing diagram of any instruction by just following the steps. Opcode fetch should be there in each timing diagram and there may be memory write or memory read or IO read or IO write, and we can join each diagram, each machine cycle timing diagram to draw the complete instruction timing diagram. So the execution time of memory read machine cycle, if we calculate it, let the clock frequency is 2 MHz, so the one time period is 0.5 microsecond. So the execution time for opcode fetch is 40 state, that is 4 into 0.5, 2 microsecond. Execution time for memory read is 3 into 0.5, that is 1.5. And execution time for one instruction, which is MVI A, 32, that is 4 plus 3, 7, those 3.5 microseconds. So we can, by this example, we can say that we can easily calculate the execution time for any instruction based on each machine cycle involved in that particular instruction. So till this point, we have covered various machine cycle timing diagrams, that is opcode fetch, memory read, memory write, which are mostly involved in each instructions, and we have combined this to draw the instruction cycle timing diagram. I hope this topic is quite clear to all of you and we will continue this in our next lectures. Thank you.